Hi students, in the second video for online lecture 15, we are now going to finish up chapter 8 and our stoichiometry with two different problem types, all coming from our percent composition. So the first thing we need to talk about is our molecular mass or molecular weight. We have seen throughout this chapter that it is the sum of the atomic masses in atomic mass units if we're dealing with one molecule, or in grams per mole if we are dealing with moles of our species. So as you can see here, we are going to have a species that is going to have the aggregate sum of our C2H6O as we are going and building this molecule. So it's important that you see that for our ethanol, we are going to take the individual masses of our components, the carbon, the hydrogen, and the oxygen, and we are going to add them together, but take into account the number of those individual atoms. As we've seen before, our molecular mass, when we are dealing with just one molecule or one element or one ion, needs to be discussed in AMUs. However, if we are going to go to molar mass, that is for 6.022 times 10 to the 23rd of an entity, then we are going to use grams. So as you can see here, one molecule of my ethanol would be 46.07 AMUs. But if I have 1 mole of ethanol, this would be 46.07 grams. The reason that this is important is that we are now going to discuss percent composition. This is the mass percent of all of our elements in a compound. So the formula that we are going to use is N times the molar mass of an element. N in this case is going to be the number of that specific element. So if we have a compound that you see below, notice that we have 1 carbon. So for our percent composition in this case, we would use the N as 1 because we would expect to have 1 mole of carbon in 1 mole of this compound. So as you can see here, here is the math and how that is completed. We will take our percent composition of carbon is equal to 1 times the molar mass of our carbon, which is 12.01 grams, and divide it by the total mass of our compound. So in the case of our methanol that you see here, that would be 32.04, and you will see that it comes out to have 37.48% carbon. We can also do the same for hydrogen, but you will see now that for our hydrogen, we will have 1, 2, 3, and 4 hydrogen atoms in our molecule. So that is why we do 4 times 1.008 grams, divide by our total mass of 32.04 grams. And you will see that even though it comprises of 4 of our 6 atoms, by mass, it is only 12.58%. So then the nice thing is we can look at our oxygen, which is colored in red. You will see that I have 1 at 16 grams. Divide that by 32.04, and you'll see that almost 50% of my mass of methanol comes from 1 atom when dealing with our oxygen. The nice part about all of this is that our percentages should add up to 100%. So if you have multiple atoms in a molecule, you can typically calculate using this formula for most of them and then just do a process of elimination for the last one. But it is also best to verify that math using the correct formula at the end. So as you see here, I have gone and verified that I have accounted for all of the mass in my molecule. So let us go ahead and try this example. Phosphoric acid, which we've seen in many of our chapters, is a colorless, syrupy liquid used in detergents, fertilizers, toothpaste, and carbonated beverages for our tangy flavor. Calculate the percent composition by mass of the hydrogen, phosphorus, and oxygen inside of this compound. So the first thing that I'm going to need to do is go and get the molar mass of the entire compound. So what I need to look at is that I have 3 hydrogens, so I will do 3 times my molar mass of 1.008 I will then need to add that to phosphorus. Notice that I only have one phosphorus, so we'll do 1 times 30.974. And then finally, we will add that to our 4 oxygens. So we will do 4 times 16, and this will give us our molar mass. And the molar mass for this compound is going to be 97.998 grams per mole. It is really important to calculate this before you do any of the individual species. So let us go ahead and start with our hydrogen. So we have our hydrogen, and you will notice that we have 3 of those. So we are going to do 3 times my 1.008 grams and divide that by our total molar mass of the compound. So that is 97.998 grams. We are going to multiply that by 100%, and you will come to find out that the total mass of this compound by percentage of hydrogen is 3.09% hydrogen. So now that we have our hydrogen, let's go ahead to the phosphorus. So we have 1 atom of phosphorus, so that is going to be 30.974. Divide that by our 97.998. We will multiply that by 100%, and you will come to see that the percent composition that is phosphorus will now be 31.61% phosphorus. If I wanted to do oxygen, I could just do a process of elimination and take 100% and subtract these two, but let us go ahead and do it using the formula just to verify that it works out. So for my oxygen, I will have 4 times my 16, which will come out to 64. Divide that by my 97.998 grams. Multiply that by 100%, and you should get 65.30% oxygen. If I were to add all of these percentages up, you will see that I end up getting 100%. So this is a successful percent composition analysis. So why do I do this? Well, for the most part, we can actually get mass percents very easily in the lab, and this can be done for us to help get our empirical formula or get our molecular formula. So the process that I will show you in this video is how to go from mass percent to the moles of each element to the lowest molar ratio, and then finally to the empirical formula. Then we know that the empirical formula is a lowest number ratio of our molecular formula. So if I were to ask you for a molecular formula, you would just have to multiply by some integer ratio. So to go from mass percent to moles, we are going to divide by our molar mass of that element. Then, once we get all of our moles of each element, we want to divide by the smallest number of moles to get us at least one species that has a molar ratio of 1:1. Then we need to look for integer subscripts, and that can be done easily by multiplying by some factor or some ratio. Let's go ahead and take a look at that. So we have ascorbic acid, which cures scurvy. It is composed of 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen by mass. Determine its empirical formula. So what we're going to do in this example is start with the information that we have. So first off, I have 40.92% carbon. I have 4.58% hydrogen. And then finally, we have 54.50% oxygen. So the percentages don't do us very well here. The best thing that we can do for our first step is assume a 100-gram sample. The reason that we do this is that if we assume 100 grams, we can change these percentages into grams. So that is the first assumption that we are allowed to make. If we assume 100 grams, we know that 40.92% of that is going to be carbon, so we just change it to grams. If we have a 100-gram sample, we know that 4.58% of that is hydrogen. We can just change it to grams and do the same for our oxygen. So now we must go and divide by the molar mass of the individual atoms. So I will get 1 mole of carbon for every 12.01 grams, and this will come out to a value of 3.407 moles of my carbon. Now I can go ahead and do the math for the hydrogen. So I can state that 1 mole of hydrogen is 1.008 grams. And now you will see that I get a number of moles of 4.54 moles of hydrogen. Let's go ahead and do the same type of math for my oxygen. So I have 1 mole is over 16 grams. And you will see that I get a value of 3.406 moles of my oxygen. So now I at least have the number of moles. I need to go to the lowest molar ratio. So what we are going to do is now select the smallest number of moles of our 3 species, which in this case is going to be the moles of oxygen. So we are going to divide by 3.406. The good part in this is this math comes out to 1. We want at least one species to have a ratio of 1. So now I can do the same thing to the other 2. So I will get my 3.407 divided by 3.406. And the nice part is that's come out very close to 1. If I go and do this for the hydrogen and divide by 3.406, you will now get a value of 1.33. So now what happens in here is that some people are going to write an empirical formula of carbon, hydrogen with a 1.33, and an oxygen, and they think that is an empirical formula. However, it is not. An empirical formula must have integer values. So one thing we can do, and how it was originally taught back in the old days, was divide by the remaining decimal, dividing by the 0.33. Now, if you're pretty good with math, you know that dividing by 0.33 is also multiplying by 3. So what we're now going to do is take our ratio that we have here, and we are going to multiply each one by 3. So I will get carbon times 3, so that's 1 times 3. I will get my hydrogen, so I have 1.33 times 3, that becomes 4. And finally, for my oxygen, I would get 3 as well. So this is the empirical formula. But let's go ahead and look at our structure very quickly here on the right. Do I only have 4 hydrogens? Well, as you can see here, I can count them as 1, 2, 3, 4, 5, 6, 7, and 8. Notice that I have twice as many hydrogens. If I do the same thing for my oxygens, notice that I will have 1, 2, 3, 4, 5, and 6 oxygens. Notice to go to my molecular formula from my empirical formula, I would have to multiply this by 2. So if I were to ask you for the empirical formula, which is what the question asked for, my C3H4O3 is a correct answer. However, if I were to ask for my molecular formula, we would have to find the ratio that we must go and multiply by, which you can see is 2. So then my molecular formula will be C6H8O3. 6.06. Let's go ahead and try our last example. Taxol is an anti-cancer drug containing 66.1% carbon, 26.23% oxygen, 6.02% hydrogen, and 1.64% nitrogen. What is the empirical formula for Taxol? Now, this may seem like a very complex problem, and it's one that we did in the fall of 2018, but this actually is a drug that I am very familiar with. Bob Holton, a colleague of mine at Florida State, is actually the one that came up with the synthesis of this, so that way they could help fight breast cancer. Bob is arguably one of my favorite colleagues and truly one of the nicest men in chemistry, so I do this as a nod to him, but it uses the exact same ideas that we have seen in the previous problems. So let us go ahead and get all of the data that we need set out first. So let's go ahead and already assume our 100 grams of our substance. So we can say that we have 66.11 grams of carbon. We can then also assume 26.23 grams of oxygen. We are going to then assume 6.02 grams of hydrogen. And finally, our 1.64 grams of our nitrogen. So let us go ahead and start with our carbon and divide it by its molar mass of 12.01 grams, and you will end up getting 5.50 moles of our carbon. In the case of oxygen, we will divide by our 16 grams, which is the molar mass of our oxygen, and you will end up with a value of 1.639 moles of our oxygen. For our hydrogen, we are going to divide by our 1.008 grams of hydrogen, and you should get a value of 5.97 moles of our hydrogen. Let's go ahead and finish up with our nitrogen. So we will divide this by 14.01 grams, and you will get a number of nitrogen moles to be 0.117 moles of my nitrogen. So which one is going to be our smallest number of moles and the one that we would like to have 1 mole of? Well, that's going to be nitrogen. So let us go ahead and divide all of these by 0.117 moles. This will turn the nitrogen into 1. If I go and do this for the hydrogen as well, you will come out to see that I will get the integer value of 51. Let's go ahead and do the same thing with our oxygen, divide it by 0.117 moles. If I do that, you get the number 14. And let's go ahead and do the last calculation with our carbon. So there is our 117 moles. And if I do this math, you will get the integer value of 47. So the nice part about this is that even though this is a really complex compound, they all come out to integer values. So let's go ahead and look at our answers, and you will see that answer D has these correct ratios. There are 47 carbons, 51 hydrogens, 14 oxygens, and 1 nitrogen. The empirical formula for Taxol is C47H51O14N. As you saw in this video, the percent composition is very important for when we are doing synthesis of new compounds, especially drugs that you see here. And it is important that you not only know how to calculate the percent composition, but also if you are given the percent composition, you know how to calculate not only the empirical formula, but the molecular formula as well. Have a great day.